Welcome to Unit 3, Lesson 4. Today we're going to be talking about translation. And by the end of this lesson, you should be able to explain translation, including the why, codon versus anticodon, genetic code and redundancy, the how, including initiation, elongation, and termination, and the who, including mRNA, tRNA, ribosome, and polyribosomes. In particular, in the first part, we're going to cover up to genetic redundancy, and that's video part 1, which is mandatory, and the rest will be in class unless you've missed class, in which case you can pick up the other parts of the video. So to start with, what is translation? Well, we've been talking about the three-part story of where we go from DNA back to DNA, which is replication, and then we mentioned how we could go from DNA to mRNA, which is transcription. That was part 2. And finally today, we're going to talk about going from the mRNA to an actual protein, which is translation. And the reason it's called translation is because we're switching our language. So we're switching from the language of nucleic acids in particular mRNA to that of amino acids to make a protein. So just to remind you, we're thinking back to Unit 2, the structure of a protein and of amino acid. First we had amino acids, abbreviated little a, has that key structure of a nitrogen attached to a carbon, with your H and your H, your central carbon with an H and some sort of R group, and then your carboxyl end with a double bonded O and an OH. So that's a single amino acid, the monomer, or building block of proteins. And today we're going to talk about how the body knows which amino acid to join to which amino acid. So we're going to talk about how ribosomes bring together amino acids in the correct order to build the protein. In other words, how does it translate from blueprint to house? And we have to remember that when we join amino acids, we form a blank type of bond. What is that? What's the other name for amino acid? That's right, it's a peptide. So it forms a peptide bond by a blank reaction. It's going to produce water. That's right, it's a dehydration reaction. Okay, and just to quickly recall, anytime we're talking about translation by ribosomes, they're going to help cause this dehydration to occur. They're going to act like an enzyme. So we'll have first amino acid, H, plus your second amino acid, you should be starting to get fairly quick at drawing out your amino acids. Coming together, and we're just going to draw, rather than beside because I've run out of room, we'll just draw the, and in this case we're only concerned with the synthesis, so the dehydration right below it. We're going to get the NCC, and it's going to attach to the next NCC. It doesn't matter whether you put the double O up or down, as long as the H on the next N is on the opposite side. And that's where we're going to have our peptide bond, is right there. That's the peptide bond. Okay, plus we're going to have brought together this OH and this H to give us our water. Okay, so the whole time we're talking about the process of translation, you have to remember that this is what we're really talking about. A ribosome acting as an enzyme to help this reaction occur, and just how does it bring in the right amino acid. Okay. So that brings us to the actual question. In general, how is a nucleotide sequence translated into amino acid sequence? And it happens because the body essentially reads mRNA as a code. And the code, it knows how to break this code, where every 3 nucleotides represent a particular amino acid. So what we mean is the body translates or reads mRNA 3 nucleotides at a time. Such that every 3 nucleotides equals what we call a codon. That represents an amino acid. Now, if we do a little bit of math, we can figure out there's many codons. Okay. To figure out how many different codons we can have, you just have to think, how many different bases do we have in DNA or in RNA? That's correct. We have 4 different bases, and if we read them 3 at a time, the possible number of codons we have is 4 to the power of 3. So 4 times 4 times 4, do your math quick, 4 times 4 is 16, times another 4, 64 codons. But these each represent how many different amino acids did we say we had? How many different R groups? That's right, to represent 20 different amino acids. So we have way more codons than we actually need. Ideally, we'd only need 20 different codons. But what this results in, first of all, 20 different amino acids, plus we have what's called 3 stop codons. These don't code for amino acids, they actually make protein translation stop, hence why they're called stop codons. So that still means we have 61 extra or 61 codons for 20 amino acids. And what happens is it means some amino acids are coded for by more than one type of codon. So one codon can only code for one amino acid, but one amino acid can be coded for by more than one codon. And this is basically, the body has a way of saying the same thing in different ways. So they can say, we want glycine in multiple different ways, glycine being a type of amino acid. When you say the same thing over and over again, but in different ways, people will often say you are being redundant, and this is called redundancy. Okay, I'm just going to pause there. We haven't quite finished the mandatory portion, but I want to make sure we don't get cut off in the middle of my explanation. So we'll just pause there, and if you could pick up and start watching part 2, that would just be a short little part. Thank you very much.